Hello friends, today we will learn about fiber testing. Fiber length is one of the most important parameters of the staple fibers, especially for making yarns. The fiber length is not an issue for man-made fibers as their length and fineness can be controlled during the manufacturing process. Cotton, wool and other natural fibers are staple in nature and their fiber length and fineness have to be determined in order to produce yarns and fabrics of desired dimensions. In general, both fibers are processed using the same machineries and often the cut length of man-made fiber influences the fiber length of the natural fibers. The measurement of natural fibers is a task which is not made easier by the fact that variations exist not only between different types of the same material but also within the same type of material. The properties of cotton fiber vary from different varieties of cotton for different regions where they are grown, different climatic conditions and from year to year. Another major problem that is faced is to express the length of cotton or other natural fibers in single value where there is high variation. This is a method in which distribution of different length group of fibers can be judged visually and numerically. It is much less laborious than single fiber method but gives a fairly accurate measurement if followed properly. In this method, a cotton sample around 15 grams is chosen to represent the bulk. Generally, in 15 grams of cotton, there are around 3000 hairs. The instrument which employs this method are bare sorter and comb sorter, which work nearly on the same principle. The 15 milligram bundle is very carefully drawn and doubled a few times till the hairs are mixed, straightened and parallelized as much as possible. It is better to make the bundle as narrow as possible and maintain the same throughout the process. The instrument consists of a bed of combs which control the fibers and enable the sample to be fractionalized into length groups. 9 bottom combs and 8 top combs are used, each set spaced 1/4 inch apart, except the first 2 bottom combs which are 3/16 of an inch apart. Thus, the distance from a row of bottom needles to a row of top needles is 1/8 of an inch. Manipulation of the fibers is done by a grip or an aluminum depressor and a blunt needle. The process of sorting is done in the following manner. First, the sorter is placed with the back towards the operator and the prepared sample is rolled or very slightly twisted and placed in the combs. At right side of the sorter as it faces the operator with a small tuft protruding. Next, by the means of a grip, all loose hairs are removed from the protruding end until there is a straight edge and the loose hairs pulled out are being placed between 2 glass slides. Later, these are reincorporated in the original sample. A tuft is now pulled from the sample, care being taken to grip the hair as near as the ends as possible. This tuft is combed several times and transferred to the left hand side of the sorter so that the coterminous ends of the hair are almost flush with the nearest comb and the tuft is straight and at right angles to the comb. The tuft is now pressed into the combs by means of the depressor. This process is repeated until all the sample of lint is transferred to the left hand side of the sorter. During this process, any neps in the sample are removed and preserved on the velvet pad. The sorter is then turned around so that the front of the instrument faces the operator and the largest hair projects towards him. The top combs are placed in the rack so as to grip the tuft and prevent uncontrolled slipping of the hairs. The hairs are pulled out in tufts by means of the grip, the longest first, the combs being successively dropped as required. The fibers are combed and straightened and then laid down on the velvet pad with the straight edged against the marked line. It is seen that a fairly accurate estimation of the length distribution can be made. Permanent records can be made either by taking photograph of the same or tracing it on a tracing paper. The figures are used to determine various parameters such as mean length, effective length and short fiber percentage. Now let us look at the process of analysis of the sorter diagram. From the comb sorter diagram, various parameters can be analyzed. In this figure, you see a typical comb sorter fiber diagram. The first parameter is the mean length. To determine the area of the comb sorter diagram using either the special transparent scale or a planimeter, divide the area expressed in square millimeter by the length of the base, that is in millimeter, to obtain the mean fiber length in millimeters. Maximum length. The length OA can be measured using a scale from the tracing. Effective length. Make geometrical construction as shown in the figure. Halve the maximum length OA at Q and draw a line parallel to the base through Q to cut the curve at P dash. Drop a perpendicular from P dash to meet the baseline at P. Next, mark off OK, that is equal to OP divided by 4, and erect a perpendicular KK to cut the curve at K dash. Half K and K dash at S and draw a parallel line to the base to cut the curve at R dash. Drop a perpendicular from R dash to meet the baseline at R. Mark off OL, that is equal to OR by 4, and erect a perpendicular L dash, cutting the curve at L dash. Effective length is the length represented by L dash. Now to calculate the upper quartile length. Mark off OU, that is equal to OB divided by 4, and erect a perpendicular UU dash to cut the curve at U dash. UU dash is equal to the upper quartile length. To calculate the percentage of short fiber. Percent short fiber equals to RB into 100, where OB is the total length of the OB. Now let us look at optical scanning methods. This is the most widely used method of fiber length measurements. Some of the instruments are digital fibrograph from SpinLab, Worcester SpinLab high volume instruments, etc. The main advantage of this method is that it is much faster than the other methods, not influenced by personal judgment, and this method can be linked with testing such as strength testing also. Sampling. A small quantity of cotton fibers is put in a fibrosampler. One of the fibrosampler combs is mounted on the comb holder with the teeth positioning uppermost. The laboratory sample is kept in the cage and pressed against the perforated surface. The pressure is maintained and the sample holder is rotated around the drum counterclockwise through 360 degrees. The loaded comb is removed from the holder. Turn the sample in the cage to expose a fresh surface and mount the fibers on another comb. Either one or a pair of combed bed constitute the test specimen depending upon the model of the instrument being used. Now let us have a look at the optical scanning of test specimens. Loaded pair of combs are inserted into the comb holders and fibers are brushed carefully to remove loose fibers. The fiber not held by the comb base, and the rest are straightened. Either the fiber combs are moved into the light zone HVI or the lighthouse is lowered Fibrograph. The fiber bed is scanned photoelectrically from base to tip. The amount of light being used to measure the number of fibers that extend various distance from the comb. The value it reports is span length. Generally, 2.5% span length and 50% span length are used for normal practice. The ratio of 50% span length divided by 2.5% span length is termed as uniformity ratio. Let us have a look at the digital fibrograph. It is an optical instrument which scans a randomly aligned tuft of fibers to estimate the length of specification of the length frequency distribution. It employs a totally new concept of fiber length called span length. The instrument is used to find out the following parameters. First one is the 2.5% span length, second is the 50% span length, third uniformity ratio percentage, that is 50% span length to 2.5% span length into 100. Fibrograph maturity. Now let us have a look at the high volume instrument. In this instrument, various properties of fibers such as length, strength, fineness, color and trash are measured. In the length measuring unit, the fiber length is measured in non-aligned fiber specimen form. The preparation of the specimen includes combing to straighten and parallelize the fibers and brushing to remove the fiber crimp. In case of motion control high volume instrument, the fiber specimen, theoretically a wedge shaped body, is lowered in steps of 0.1 mm through a slot into the vacuum chamber. The vacuum in the chamber increases as the slot is closed by the wedge shaped fiber tuft. The change in vacuum is proportional to the increasing fiber mass in the fiber wedge. An extremely sensitive sensor converts the changes in the vacuum into electrical signals. The length characteristics reported are upper half mean length, uniformity indexed, short fiber content and also span length. Uniformity index is the ratio of mean length and upper half mean length expressed in percentage. So, the formula is uniformity index would be equal to mean length divided by upper half mean length into 100. Short fiber content is given by the percent of fibers by weight which is less than half an inch. Now, let us have a look at the AFIS method. The AFIS method is based on aeromechanical fiber processing similar to opening and carding, followed by electro-optical sensing and then by high-speed microprocessor based computing and data reporting. A fiber sample is introduced into the system and processed through a fiber individualizer which automatically separates the sample into 3 components consisting of clean fiber, microdust and trash. Each of these components is transported in a separate pneumatic path and may be analyzed electro-optically or by other means. The data processing and reporting are handled by an industrialized PC. AFIS provides single basic fiber information and is distinguished from to the methods by providing distribution of the basic fiber properties. Now students, let us have a look at fiber fineness. The fineness of a cylinder may be expressed as diameter. In the earlier days, the quantity invariably used for defining the fineness or coarseness of a fiber was diameter. For wool, which is nearer to circular in cross section, this is reasonable enough. And for modern synthetic fibers also it can be used. But most of the natural fibers are neither perfectly circular in cross section or nor uniform across the length. The mass of known length of a fiber is termed as linear density and this can be expressed as weight per unit length. The widely used units are micron, that is microgram per inch, denier, weight in grams of 9000 meters, tex, that is weight in grams of 1000 meters, decitex, weight in grams of 10,000 meters. The fineness of a fiber is very important as it decides the number of fibers per cross sectional area of a yarn and this decides the yarn strength and irregularity in general. The basic principle of this method is to count the number of fibers of a given bunch, measure the length and weigh them. Consider a cylindrical material. The linear density can be calculated by using the following formula. F is equal to N into L into M, that is divided by 9000 into 100. Here F equals linear density, N is the number of fibers, L is the average length of the fibers, M is the mass in grams. In practices, very few natural fibers are uniform cylinders. For man-made staple fibers, it is a standard method prescribed by BISFA. The lengths of individual fibers are measured and the fibers are preserved and weighed. The formula described before is used to calculate the linear density. Fibers like cotton have got non-uniform diameter along their length. Both tips are thinner and the center portion is thick. Also, there is a large variation in fiber length. In this case, the above mentioned method might not give right values. In the method described by ASTM, about 100 fibers are taken from each of the sorter web sorter groups and weighed, from which the weight per unit length of each group can be obtained. The average fineness can then be calculated. Indian standards has included two methods for determination of linear density of textile fibers by gravimetric method. The first one is the cut fiber method, that is the middle part of the comb tuft is cut a given length under the minimum tension necessary to remove the crimp, and then around 1000 fibers are taken out from them and weighed. The linear density is calculated from the weight and total length. The method necessitates several precautions. First, the tuft should be conditioned before weighing to avoid error due to different moisture content. Next, the weighing balance should be highly accurate. Accuracy of 0.02 milligrams is expected. The second method is weighing of the whole fibers as described earlier. It was observed by few workers that the fiber weight per inch varied with different group length of fibers, but the extent of variation was not the same in all varieties of cotton. Also, there is a possibility of fiber weight per unit length being variable along the length of a fiber. In the cutting model, 1 cm lengths are cut from the middle portion of the bunch of fibers after fibers are straightened out. If the central portion weighs more per unit than the end portion, which is typical of cotton fibers, the result given by the cutting method will be higher, and if it weighs less, the result will be lower. It was observed that in case of cotton, whole fiber method saves lower values than the cutting method. If the weight of the fiber is noted at a relative humidity other than 65%, the value of the fiber weight determined at any relative humidity percentage has to be multiplied with an appropriate correction factor. Now, let us have a look at the microscopic method. In this method, fibers are mounted on the microscope and the diameter is measured after magnification. The fibers which are not circular in nature cannot be measured by this method. For man-made fibers which have circular cross section such as polyester and nylon, this method might be applied. For wool, this method is used widely. Due to variation in diameter, a large number of samples have to be observed to get a representative value. Since it is a time consuming method, the latest instruments measure the diameter of 5000 to 10,000 samples in a minute by using microprocessor. In this method, samples, that is the fibers, are placed on the platform and the microscope is used to magnify the images. These images are analyzed and the fiber diameter as well as linear density is calculated automatically. Now, the next method that we are going to have a look at is the airflow method. The measurement of the fiber fineness by gravimetric method and most optical methods are slow and tedious. Therefore, these methods are unsuitable for use in mill routine work. An alternative method has been developed using indirect path to measure the fineness. These instruments are based on the airflow principle. A sample of known weight is compressed in a cylinder of known volume and subjected to an air current at a known pressure. The rate of airflow through the compressed samples, that is the porous plug, is measured. The flow meter is often being calibrated in terms of fineness instead of volume per unit time. Example, microns for wool, microgram per inch for cotton. Preparation of the test specimen. The cotton fibers should be opened with fingers by breaking up of the lumps if any and by eliminating extraneous matter as much as possible. Then the sample should be conditioned at standard conditions from the opened, clean and conditioned cotton fiber. Approximately 25 subsamples are to be made. From each subsample, small bunches of loose fibers are to be collected, removing all the non-fibrous material that is present. Those clean small bunches are mixed together and 2 specimens are made for testing. 4 tests from those 2 specimens. Testing of the micronair value of cotton. Air under a specified pressure is passed through a specimen of cotton of known weight confined to a space of known volume. The mass and volume of the specimen may be either constant or varied in relation to each other according to the type of instrument used. The resistance of the specimen to the flow of the air is related to the average fineness of the fiber in the specimen. The rate of flow of air through the specimen or the pressure difference across the specimen is indicated on a scale graduated in either arbitrary units of micronair value of appropriate absolute units. Micronair testing by Sheffield Micronair. This instrument was first conceived by Smith and production of the development was carried out by Sheffield Corporation. A representative sample of 3.24 grams is worked into a loosely fluffy mask before being packed evenly into the cylindrical holder at the front of the instrument. A plunger is then inserted, depressed and locked into place. This compresses the fiber into the form of a cylindrical porous plug 1 inch in diameter and 1 inch in length. The bottom of the sample holder and the end of the plunger are perforated so that when air from the compressor passes through the filled holder, the fibers offer appreciable flow resistance. The vertical part of the instrument is fitted with a tapered glass tube and containing an lighting indicator float. When the air passes up the tube and hence through the sample holder, the float rises to a height depending upon the rate of the flow. This rotameter type of flow meter is not calibrated directly into units of flow, but it is calibrated on the basis of experimental work on the samples of American upland cotton. The scale has been marked in terms of fiber weight in micrograms per inch. Other instruments mentioned work under the same principles. In Atira and Citra, fineness testers and calibrations that are done by using Indian cottons.